Let's have a look. Right, guys, we're going to have a look at a physics tutorial. So, yeah, no, why not? So, what do I need to start with? Thermodynamics one.
Yeah.
Okay. I've uploaded to YouTube all the answers up until the ideal gas law. Which lesson did you want the answer for? That's up on YouTube, you can get the answer. Right, you said the thermodynamics lesson.
Yeah.
Okay, which question? Number 2. Oh yeah. Coal is burnt, and as such, Q joules of energy is given to a steam engine. The engine produces W joules of work, while at the same time the internal energy of the engine increases by delta U. What is the efficiency? Yeah, it's just going to be a formula like this. So you have the engine, and Q energy goes in from the coal, and as a result the engine does W of work, and then there's an increase of internal energy. And the formula we know is the increase in internal energy is equal to Q minus W. Now the efficiency is the work out over the work in times 100. Here the work out is W, and the work in is Q. And Q is W plus U. Now, this is actually an important result, because it means that the efficiency should be less than 100%, because this part here will always be bigger than this part here. So this is actually an important result, a result you already knew. Okay. Continue? Continue? What's next?
3.
Just straight on to the next one then, yeah? Okay. Number 3. A piston of radius 4 centimeters and height 10 centimeters. 4 centimeters, 10 centimeters, and you put some heat into it. How much? 200 joules. How much work was done if there was nearly no change in internal energy? So you have a Q equals, sorry, what am I saying? Delta U equals Q minus W. But I said delta U is nearly 0. Now, in real life it's not 0. That's why I said it's nearly 0. So that means Q should equal W, which means 200 should equal W. So the answer is just 200 joules. How much work was done if the piston was 50% efficient? So the reason it's 50% efficient now is because we can't ignore this. Some energy is wasted into internal energy. So you can actually, if you think about it, that formula we just got previously would be useful. So now I have 50% equals work over work plus delta U times 100%. Yeah, so if you rearrange this, you'll get basically W equals delta U. Well, just by solving this, you'll end up with this result. So we know that W equals delta Q, and what were we looking for? The W. Or the output W, I suppose, to be more accurate. So if I go back to this formula here, I get delta U equals Q minus W. W equals 200 minus W. 2W equals 200. So in the second question there must have been 400 joules of work. Oh, sorry, 100. sorry, 100. Yes, yeah. Whatever makes you happy and helps you sleep at night. Okay. 4. A gas is in a cylinder of radius 5 and length 100. The gas is heated by 100 joules. In addition to this, the cylinder is compressed by 10 centimeters by a force of 1 kilonewton, both providing heat and doing work on the gas, causing it to gain internal energy. How much energy does it gain? Okay, delta U equals Q minus W, and I want the delta U. Do I know the Q?
Yeah.
What is it? No, the Q. 100. And work is force times distance. But force is pressure over area. Yeah. Oh, do you actually have the force? You don't need to worry about the pressure.
1 kilometer.
Do you have the distance?
Yeah.
Oh, great. So this is 1,000 times 0.1. So it looks like it's 0. But this is where, not that I made a mistake, I have to remember something that I said in the question. The work is done to the gas, not by the gas. In fact, this here is a minus, because the work is the other way around in this story. Normally, the engine is doing work, so the work is coming out of the system. But in this example here, I said the work is done to the gas, so work is going into the system. Because of this opposite direction, it's a minus. You don't get 0 now, you get 200. Yeah? There's no calculations in number 5. I just want you to think about the logic here. Oh, I just gave you numbers that were completely irrelevant because none of my questions was oh, well, the A was, I suppose. Yeah. The answer for A is 100 kilojoules. Well, 100 kilojoules went in, and the change in the internal energy is 100 kilojoules because the kettle's not doing any work, it's just sitting there getting warm. Yeah, and that's the internal energy. The internal energy is the heat in the water. So it's 100 kg. 100 kilojoules. What?
More like that.
No, it's because
No, that's not the work. In this thermodynamics equation, the work is something like a machine, in the sense like an arm is moving or something is happening. The internal energy is the heating. No. B, another 100 kilograms of heat is added and the kettle starts to shake. Will the internal energy be the same? No, it'll be more or less? Less? Because... yeah, because this now is not zero, so this is the same. This is the same and this is increased, so the result is this is decreased then. The heat is turned off but the kettle continues to shake. What is the change in internal energy? Well, if the heat is turned off, you get this. So the internal energy is a negative. That's all I wanted you to say for that one. The kettle falls off the stove and hits the ground. Will it be hotter or colder when it hits the ground?
Colder.
Be hotter. Why will it be hotter? Here's the kettle and it hits the ground. It has potential energy here. Then it has kinetic energy. Then when it hits the ground it has no potential or kinetic. So the potential became kinetic, but then what did the kinetic become? The kinetic, in the end it'll be heat. It became work. So in your formula, delta U equals Q minus W. There is no heat, so you have that. So delta U equals minus W. But the kettle is not doing work. We are doing work to the kettle. In other words, we took the kettle and we hit it on the ground. Huh? Well, I mean, in essence we did. When we knocked it off the table, it's like, just hitting it on the ground. Someone just took the kettle, it's on the edge, and just pushed it off. The same as taking it and just hitting it on the ground. Well, same thing, it just fell off. So, work was done to the kettle. That means that's a minus. In fact, minus mgh.
How can it be minus?
I just told you I said work is being done to the kettle, not the kettle is doing work.
Well, how it can be minus? It's not changing the direction.
No, it is. In this formula, this is the work out.
Yeah. This
is the work that comes out of the kettle. So for example, if there's steam coming out of the kettle and it turns a wheel, that kinetic energy, that's the work that comes out of the kettle. If I take the kettle and do this or throw it, I am putting my effort, my work into the kettle. So the sign must be different because it's the other way around. It can't be the same. I'm putting energy in. Another way to think about it is, where did this energy go? It didn't just disappear, it had to go somewhere. So I'm saying that the energy went into making the kettle warmer. mgh. And this, you can actually see this in real life. If you go to the bottom of a waterfall and measure the temperature of the water, it will be warmer than at the top of the waterfall. So if you look here, let's say we have a waterfall that's 100 meters, and let's say we have 1 kilogram of water here, and I measure the temperature, and then I measure the temperature at the bottom of the waterfall. The water's flowing down. Well, this will have potential energy. This has no potential energy. So the potential energy actually became heat. So you actually have this formula, mc delta theta equals mgh. We can cancel the m's. We get delta theta equals 9.81 times 100 over 4181. So that's roughly going to be roughly 1,000 over roughly 4,000. Yeah. Roughly 0.25 degrees warmer at the bottom of the waterfall than at the top. In fact, it was Joule who did this experiment. He went to the top of a waterfall, put the thermometer in, measured the temperature, climbed down, put it into the bottom of the waterfall, measured the temperature, and he saw it was 0.25 degrees warmer. It's the same idea with my kettle story, except it's not fallen 100 meters, it's fallen 1 meter. Yeah? You don't like this lesson, I can see. I can see you don't like it. That's a good thing. Imagination is important. I'm going to give you, I added in one more question to this lesson that I'd like you all to try now. I think who was asking me about a week ago, or this week, is there a maximum temperature? Who was asking me that? You were asking me that. Inspired by your question, I added in one extra question about this. It's good. I was inspired by this. He inspires me. So, let's have a look at this extra question I added in. Is there a maximum temperature? Let us estimate. Okay, let's do this together. So I'll give you 1 minute, part A. In the formula, T equals 2 over 3K KE, average. Why did we have the 3? So remember, about a week ago I proved the formula, and I said the proof is too big for the exam, but you should understand the proof. This is a good example of that. You can look at the proof again now if you want. I want you to tell me, why did I get the 3? In other words, where did the 3 come from in the formula? So have a look at that proof. You remember the proof that gave me, I'll show you here. It was E equals 3 over 2 PV. I want you to look at that proof and in a minute tell me where the 3 came from. Let's give everyone a minute to look. You think you know though? Yeah, but why 3 and not another number? That's my question. Yeah, very good. That's it. Just write one sentence. The 3 was due to the fact that... Yes. Lee, did you get the answer for part A?
No.
Are you looking at the proof?
Yeah. I'll change the 3.
Yes. Very good. Okay, so we figured it out. The answer is, in T equals 2 over 3KE, or KE if you want, the 3 was because we were in 3 dimensions. Yeah? Now, if I'm trying to figure out what is the maximum temperature, so now I'm on to part B. If I want to know what is the maximum temperature, then do I want to make this bigger or smaller?
Smaller.
Smaller. Can I change the 3 into a smaller number? I can. No, I can. What's the smallest I can make it? 1 dimension. I can do this if I put my molecules into a very narrow tube so that they're only able to move left and right, but they cannot move up and down or back and forth. So if I can do this, then I'm getting closer to working out the maximum temperature. It'll be 2 over 1K, and then this is kinetic energy, remember. So that will be 2 over K, a half V squared, where the V is the vibration here. So that will equal mv squared over this constant K. Okay, good. We're getting closer now. we at least know this, but we don't know this and we don't know this. Okay, but somebody might know this. There is a limit to how big the V can be. The V can't be any number. There's actually a limit to how fast something can move. Does anyone know what that limit is?
Oh, there is a limit.
There is a speed limit. There is a maximum speed you can travel at, and you cannot travel faster than this.
Light.
Yeah, you cannot travel faster than light. So C is 3, or 2.99, 3 times 10 to the 8 meters per second. This is the speed of light, and this is the fastest anything can go. So now we're at this formula, mc squared, and we know the c, over k. Good, getting better. So we know k, we know c, we need to figure out what is the biggest the mass can be.
No.
There is actually a limit. And the limit is because
Ground zero.
this is not the limit. When we have a small space like this for our molecules to fit in, there's only so much we can actually fit in to a space so tight we don't let the molecules move up and down and back and forth. So when this is small enough so that this can only move left and right and not up and down, there's a limit to how much you can actually, fit into it. You can't put any mass in there. There's only so much you can fit in. And in fact, that limit is something that I already gave you, but at the time I didn't tell you what it was. And it was all the way back in the very first lesson, the very first worksheet. The most the m can be is 1 Planck mass, which is something I gave you in the very first lesson as a question. I never actually told you why those units were important. Do you remember Planck length, Planck time, and Planck mass? Planck mass is actually the biggest you can actually fit into this space. And you can probably guess now what a Planck length is if you look at this example. What do you think the Planck length might represent? And remember, it's a small number as well.
1.
No. The Planck length is actually this distance. So in other words, Planck length is like the smallest tube you can make, and the Planck mass is the biggest mass you can fit into this smallest tube that you can make. Anyways, you now know these 3 terms, so let's calculate it. Now I need to look up Planck mass because I forgot it.
So the answer there is limit, right?
Well, let's calculate it. So Planck mass is 0.02 milligrams. Milli is 10 to the minus 3. Grams. Oh, I wanted kilograms, not grams. Yeah, isn't it? Well, we'll put it like this. 2.176 times 10 to the minus 8 times 3 times 10 to the 8, isn't it? Or 6? 8. Squared. And then what was the Boltzmann's constant we had a few lessons ago?
1.38 times 10 to the power negative 23.
Okay, hit this in, Lee, and you can tell me what is the maximum possible temperature. So temperature now must be more than 0 Kelvin and less than
1.42 times 10 to the power 32.
Kelvin. And If absolute cold is 0 Kelvin, then we actually call this absolute hot. So we actually have limits on our temperature from 0 Kelvin to 10 to the 32 Kelvin. This is a very large limit. How hot is the sun?
In Kelvin.
In Kelvin it is 15, so in Kelvin it's 15 million Kelvin.
Wow.
So you can see that this is still not that hot compared to the limit. It's tiny compared to it. So don't worry, Lee, we won't reach this limit. This is more a theoretical limit, not a realistic limit.
Teacher, it's not enough. 2 more, okay.
It's not enough to what?
2 more.
What?
2 more.
2 more? 2 more what?
1 more is this one. Yeah, to multiply 10 to power 23.
Yeah?
And this is not enough. 2 more.
Okay. I'm confused. I'm so sorry.
It's temperature.
Oh, okay. So I think, Lee, I think it's interesting. It's interesting because we don't really think about a maximum temperature because it's so far outside of our experience. When you think about it, we're much closer to being at absolute cold than we are at absolute hot. So it's not really something to think about much. Yes. Which is next now? Okay, specific heat capacity now, yeah? Did I not? That is disgraceful of me, I'm sorry. How much whiskey will we put into our water? Equal parts whiskey and water. 500 grams of whiskey and 500 grams of water is one strong drink. Let's make it 50 grams.
Yeah.
Shall we make it 50 grams?
Yes.
50 grams.
Number 2. I never told you how much whiskey there was.
So
anything else that was missing from that lesson, Monica? So guys, just so you all know, here in the lesson yesterday, I didn't tell you the mass of the whiskey. Can you write in 50 grams? It's 50 grams. You got that? Yeah. Sean, have you got that? Sean? Did you write down 50 grams? This is 50 grams. I didn't tell you that yesterday for this lesson.
50 grams, 50 gram water, 50 gram whiskey, 500 grams water.
I think 50 grams whiskey with 500 grams water sounds like a fair mix to me. What did you tell her? 500's too much?
No. I calculate to 100 grams and 50 grams. In case of you do 100 grams when I do 50 grams. Yeah, so
You felt like I would pick 50 or 100. Yeah. You know my style. Guys, come here, listen. Jerry.
no more GS.
No, yeah, it's beer.
I'm glad you're proud of this. Good. You remember that your class has moved to 12.
Yeah.
Please bring your laptops. I think I might help the people who haven't finished yet, and maybe I'll have Connell help the people who are finished. So I'd like Connell to read and give you feedback on your essay. Well, good thing you have an hour free now. Boom! See you later.